Hello everyone, my name is Kashish Arora. I'm at CUHK Business School. Our research is set in the context of Indian Railways, which is the fourth largest railway network in the world. As of 2025, it transported about 8.1 billion passengers and carried 1.4 billion tons of freight annually. Our specific research question is about freight train speeds in the Indian railway network, which have remained extremely low during the past few decades. And these slow speeds have actually led to a decline in the share of railways in inland transport. Now, this is quite problematic because railways are essentially one of the most economical and sustainable forms of transporting freight. And the reason for this slow speed is because freight trains essentially share network capacity with passenger trains in the Indian railway network. And whereas these passenger trains are scheduled, freight trains remain completely unscheduled in the Indian railway system. Due to this, passenger trains get priority in movement, which leads to huge amount of freight delays in the system. And these delays are actually extremely costly. Some empirical estimates have pegged the cost of these delays to be around $800 per hour per train. And you can imagine with the scale of Indian Railways, these delays are actually incurring huge monetary costs on the system. Accordingly, our research question is how to reduce these delays in the Indian freight railway network. Now, one natural question is who's making these delay decisions for freight trains? It turns out that freight train movements are actually managed manually by railway staff that are known as section controllers. These section controllers essentially manage a group of stations and manage the movement of freight trains in and out of the stations. So think of them as air traffic controllers, but for freight trains. And our goals in the paper are twofold. One, we need to understand how these section controllers make freight train movement decisions. And two, we want to investigate policies that help reduce these freight delays. Now, there are two types of decisions we consider in this paper. One, if a train is moving, the section controller needs to decide whether to stop it at the next station or no. We call it the stop pass through decision. Two, if the train is dwelling, the controller needs to decide whether to continue holding it at the current station or no. This is known as the hold release decision. The figure here shows how one stop decision and three hold decisions lead to a total delay of 4 minutes for a freight train. Now, these are the things that we do in this paper. So, to understand controllers' decision making, we first provide model free evidence that shows that these decisions are affected by the state of congestion on the network. Two, we then build a structural model of controllers' decision making that actually incorporates these congestion features into their decision making. We estimate this model while addressing endogeneity and econometric challenges that arise due to the spatial correlation that exists in our data. To investigate policies, we actually perform counterfactual analysis. We consider two types of interventions. One is the capacity intervention, which involves creating a dedicated freight corridor. And we also consider non-capacity based interventions, which are not as costly as the capacity interventions. Our paper uses highly granular data. Specifically, we're using minute by minute snapshots of network congestion, which is defined as the number of passenger and freight trains on the network. We essentially have a binary choice model where the section controller decides whether to hold the train or no, and her utility actually depends on a rich set of features that are described here. But this is not just a simple logic model. In fact, the model can be quite complex because these controller decisions are essentially correlated over the network. And we use copulas to characterize some of these correlations. The other challenge here is that one could have unobservables that lead to endogeneity. and we have network instruments to correct for that. And you'll see some of these elements in the longer version of the talk at Informs. Now, we basically evaluate two types of counterfactual policies. The capacity intervention involves setting up this dedicated freight corridor, and the government of India plans to spend about $10 billion constructing this. In the non-capacity intervention, we consider threshold releases where one could release the freight train if their dwell time passes a certain threshold. We also consider double stacking, where you essentially have these double decked trains, which essentially reduces the number of trains in the system while maintaining the same load. And the main punchline of our paper is that some of these non-capacity interventions, which are highly cost effective, can also yield significant speed improvements when compared with the capacity interventions. For example, the threshold releases give us a speed benefit about 5 to 9%, and double stacking gives a speed benefit of 10%, which captures a large part of the benefits that the freight only corridor captures without incurring billions of dollars in cost. So it's a win-win situation for Indian Railways. Thank you, and I look forward to seeing you for the longer version of talk at Informs.